we have been talking about the concept of drying and how important it is. The most important picture in the drying process is this one. So in the x axis you have a moisture content and in the y axis you have the rate of drying. So initially you have plenty of water present on the surface of the solid. So drying takes place as the liquid starts evaporating or the solvent starts evaporating. So the drying is constant, that is why this is called a constant rate drying. So here the only factor that is limiting is how much heat you are able to supply so that the material gets dried, that means or the liquid gets vaporized. So the rate of evaporation is matching with the heat of vaporization, which is also equal to the driving force, which is the vapor pressure of water to the partial pressure of water at that temperature condition. Now once the water starts drying from the surface has only less amount of water, more water is present in the interstices or in the pores. So there has to be some water which needs to diffuse out of these pores, come to the surface and then gets evaporated. So what happens in that time, the rate of drying starts falling down, and that is what is called falling rate period. So as time progresses, the water which are found inside has to diffuse out and then get evaporated. So it becomes slower and slower and slower, and that is what is called the falling rate period here. So initially you have a constant rate period and then the rate of drying falls down as a function of time. Finally the amount of moisture present in the solid reaches an equilibrium value with the surrounding air. So the surrounding air contains certain relative humidity. So this particular moisture content is called the equilibrium moisture content. So this equilibrium moisture content is the concentration of water in that material present, which is in equilibrium with the amount of water present in the air at that particular temperature. Okay, you cannot dry the material below this water concentration unless you change the relative humidity of the water. Okay. Now the constant rate period and the falling rate period are separated by something called the critical moisture content, that is the moisture content until which the rate of drying is constant and below which the rate of drying keeps falling down with the time. So that is called the falling rate period. So you have a constant rate period, you have the falling rate period, and in between you have the critical moisture content, and finally you have the equilibrium moisture content. Now the time, overall time required for drying a material starting from some initial moisture content to some final moisture content, equation will look like that. There are two terms in this equation, one is related to constant rate period, other is related to the falling rate period. So this corresponds to the rate of drying where the driving force is difference between the initial and the critical moisture content, whereas this one relates to the falling rate period. Okay. So this is how the time required to dry a material can be calculated using this particular equation. It is a very useful equation if we want to design dryers and if you want to find out what will be the batch time for drying a material starting from some concentration to some other concentration. So you can see that if I increase the area here, the drying time goes down, if the mass ms is increased, drying time goes up, and so on actually. Okay. So drying is a very important unit operation which is practiced in chemical industry, pharmaceutical industry, biochemical industry and so on. This is generally the last step in the downstream process. So one important point which we need to keep in mind is the temperature sensitivity of the material. If the material is very temperature sensitive, we cannot afford to increase the temperature, so we apply vacuum so that the temperature does not go up too much. Now analogous to drying using temperature, we can also remove water or moisture from a solid using something called freeze drying or lyophilization. Okay, this is practiced quite a lot in the area of biological systems because they are highly temperature sensitive. So that is called the lyophilization. So let us look at lyophilization in detail, and we will look at also what are the parameters that contribute in this particular process. Okay. So what is lyophilization? It is also called freeze drying. That means we are removing water from the frozen material. So if you freeze a material with the water present, so what happens? The water becomes ice, the material also gets frozen, and then when you change the temperature or when you change the pressure, the ice directly goes into the vapor. So it does not go into the liquid at all. So you select so that, okay, you select operating condition so that the ice directly goes into vapor and it does not go through the liquid phase. That is what is called freeze drying. So what do you do in a freeze drying? You cool it sufficiently so that everything gets frozen including the water, and then you change the pressure or reduce the pressure or increase the temperature so that ice directly goes into vapor, it does not become the liquid. So it is a very good method for preserving microbes, heat sensitive materials such as proteins, plasma, for example blood plasma, nothing like doing a freeze drying. Okay. So in a freeze drying we control both temperature and pressure. So for example, if I have some pharmaceutical product in vials, I can use the freeze drying technique to remove the water or moisture present, at the same time keep the vials in a sterile condition. So that is the advantage of using a freeze drying in pharmaceutical setup. Now this is called a phase diagram for water. So in a phase diagram we can see where solid ice is present, where liquid water is present, and vapor is there. Okay, water vapor is present. So you have all three of them together. Okay. So like you have the solid, you have the liquid, and we have the vapor. So as the pressure is increased, you have the solid region, and as the temperature is increased, you have the vapor region, and then in between you have the liquid region. Now if you look at this, there is something called a triple point, okay, where the solid, liquid and the vapor meet. Okay, this is called the triple point. This is at 0.01 degree centigrade and 4.6 mm mercury. Okay. So if we are operating here, we have to, if we want to move from solid to liquid to vapor like this, whereas if you are operating here, you can see that I can directly move from vapor to solid or from solid to vapor. I do not have to go through the liquid at all. Okay. So if you are here somewhere and you want to go to solid, you have to go through liquid, or if you are here from solid, you have to go through liquid to vapor, whereas if you are operating here, you can directly go from vapor to solid or solid to vapor. Okay. Now there is another point that is called the critical point, where the liquid and the vapor meet. Okay. And this region is called the supercritical fluid. You must have all heard about supercritical fluid, supercritical CO2, supercritical water, and so on, actually, you know, where the fluid behaves like a liquid or a gas. So it has got both the useful properties of the liquid as well as the gas. So supercritical carbon dioxide has become very, very important, and we also talked about it long time back in the extraction process, where supercritical carbon dioxide can be used very effectively for extracting natural product, metabolites, or useful chemicals from phytochemicals, where you do not need to use high temperature, which may denature or deactivate such sensitive material. So supercritical fluid region is this, where you are operating above the critical point, where the liquid and the vapor behaves like a supercritical fluid. Okay. So that is supercritical fluid, whereas at the triple point here we can move from vapor, that is water vapor, directly to ice, solid ice, or we can move from solid ice to vapor. So if you are operating in this region, if you are doing a lyophilization, so all you need to do is you reduce the temperature so that the ice is formed, and then you play around with temperature and pressure so that the ice directly goes into vapor. So by doing this alternatively, we can slowly remove whatever water is present to a vapor form. So in this process you are not increasing the temperature unlike drying, so the material which needs to be dried is completely being operated at low temperature, so it does not get denatured. It is a very useful technique, especially for proteins, especially for plasma and so on actually. Okay. So what are the various steps in freeze drying? So what you do is you first cool the product to a sufficiently low temperature. So by doing that you are completely solidifying or converting the material into a solid form. Then what you do is reduce the pressure in the chamber to below the vapor pressure at the triple point of water, so that there is sublimation. What is sublimation? You are converting solid into vapor, that is what is called sublimation, right. So you are converting the solid water into vapor water. So what you do, you reduce the pressure. So initially you are reducing the temperature and then later on you are reducing the pressure, so that solid ice becomes vapor. As I said, the triple point, the ice, water and water vapor exists in equilibrium at 0.01 degree centigrade and 4.6 mm mercury. So below this triple point, water passes directly from the solid to the vapor phase, that is sublimation takes place, so no problem, you do not the ice does not go as water. Okay. So by doing this we are removing all the unbound water, so that is called the primary drying. Now later on we need to remove the bound water, so what do? We slightly raise the temperature and keep the pressure down. Okay. So by doing this then we are removing the bound water, that is called the secondary drying phase. So initially you have the primary drying phase where by reducing the pressure you are operating below the triple point, so the solid ice goes into vapor, and in the second phase we are keeping the pressure down but slightly increasing the temperature, so that the bound water gets removed. Okay. So these are the two steps. So we have the primary drying and we have the secondary drying, okay, to remove the unbound and the bound water respectively. So generally in a supercritical, the time required to complete the drying cycle is about 24 hours, even 48 hours. In the labs sometimes we take more than a day to completely remove the solid. So once you do this sort of lyophilization, there is no water present, there is no liquid phase. So reactions like hydrolysis, cross-linking reactions, oxidation reactions, aggregation of the solid material, disulfide rearrangement, all these are prevented. Okay. And also when you dry the product completely, it has got much higher surface area per volume. So if you want to redissolve it into some solvent, then it is very rapid and complete. So that is the advantage of lyophilized product. Okay. So the three steps in lyophilization, we have the freezing. Okay, sample is placed in a freezing vial or flask. So in a laboratory situation we take the material in a flask. If you are working in a pharmaceutical industry, you take it in a vial, because it becomes easier for you to completely seal it once you have done the freeze drying. And then next step, once you have frozen the material, what do? You are by sublimation you are removing the solid material into vapor. So 90% of the total water in the sample goes away. Okay. So some of the free water and some of the bound water goes away. Then what do? We are now desorbing whatever water is present by increasing the temperature. Okay. So finally by doing that you will end up with about 1 to 3% residual water. So this step also takes some time, it almost 50% of the time it is taken for removing the unbound water, so you need some time for that. So the final step of this lyophilization, we call it desorption, or we call it secondary drying or drying to remove the bound water, like that, so you reduce the moisture content to almost 1%. So there is a lot of water which is present on the product in the form of a shell. Okay. So it is a surface phenomena, it is not a water of hydration, but it is more of a you should not confuse the removal of bound moisture as removal of water of hydration. So it is more like water present in the form of a shell like. So you have to go up in temperature to about 30 to 40 degrees centigrade, and may take about 4 to 5 hours actually. And if you are if you have a wild pharmaceutical product, then you may slowly form ice cake like. So generally the cake thickness may be of the order of 1 centimeter. Okay. So there are different types of freeze drying. One is called the manifold drying. So we have a central manifold, so you attach many ampules or drying flasks to the central manifold, and then the samples are frozen, okay, by the shell method. Okay, first the samples are frozen separately, and then they are attached to the manifold, and then you are applying the vacuum prevent melting, and then you bring up the temperature. So there is a room temperature provides the heat. Okay. So generally this type of method is very good for small volumes. So first freeze all the flasks separately, and then they connect it to the manifold. Manifold is placed under vacuum to prevent melting, and then you raise the temperature to room temperature. So this heat is sufficient to remove the moisture directly. The ice goes into vapor. This is very good for small volumes. Okay. If you are talking about bigger systems, then we can use a tray type of arrangement, and then there could be heating elements in the tray to supply the heat. Okay. So we can have similar type of containers. You can cool them all, freeze it like serum vials, and then keep it on the tray, and then you apply a heat, and thereby you achieve the drying process. If you have large volumes of a single sample, then what do? You can pour the material in special trays, freeze it, and then dry it in a lyophilizer. But one thing is, you cannot take these samples and again seal it separately, because if you are going to do that and you are exposing it to air, sometimes the oxidation may affect the product quality or product stability. So if you are talking about not exposing the material to outside atmosphere, the best method is a manifold drying or a vial drying. So you take the samples in hundreds of vials, freeze it, connect it to a manifold, apply vacuum, slightly heat it up, so all the moisture is removed, and then you can seal the vials or flasks. So that is the advantage of that type of setup. Whereas in this type you can handle large quantity of material, but some amount of exposure after lyophilization is inevitable here. So what are the factors that affect lyophilization? The sample size, how much material I am handling, surface area of the sample, is it having a big surface area per volume, or the surface area per volume is less, thickness of the sample, because as you know the solid ice has to convert into vapor, and if you have a thick ice formed, vapor has to diffuse and go out. Sample characteristics, that means physical properties, viscosity and density and so on. Eutectic temperature, because what is eutectic temperature? We are talking about solid ice and solid material. So these two can together combine to form a third blend of product. That is where eutectic temperature comes into picture. Okay, because you have ice going into solid, you have the actual material, protein or any other chemical that is going to be frozen. So both of them may dissolve and form another third phase, and that is where eutectic temperature comes in. Solute concentration, how much of solute is present in water. Then the instrument factors, what are the various instruments which you are using. Then the condenser temperature, you are going to ultimately take out the vapor and condense it again. So what is the temperature, and how much vacuum you are applying. All these factors affect the lyophilization process. Okay. So larger the surface area of the frozen material, faster will be the rate of lyophilization. This is obvious. So if I have large lyophilizer area, then we can do the lyophilization process very fast. Thicker the frozen material, slower the rate of lyophilization, right. Again, when you have thick material, the vapor that is formed when you apply vacuum and heat it, that vapor has to pass through this thick frozen material before it can be collected in the condenser. So that process is going to be slow. So thicker the frozen material, slower will be the rate of lyophilization. So sample thickness affects the ability of a sample to absorb and transfer heat to the surface undergoing sublimation. So ideally I would like to spread it out on a large pan, so that when the lyophilization is fast, the thickness is also less, that is the frozen thickness. Whereas if I have a very small container, the area for lyophilization decreases, so sublimation is slower, because the vapor has to diffuse through the thick solid icy material, because the water vapor must pass through the dried material, and the rate of lyophilization in thick sample is slower, especially if the dried material collapses on the surface of the frozen material. Suppose the dried material forms a shell like, and as it gets dried it may just collapse, thereby slowing down the diffusion of this vapor out into the vacuum region. Okay. So if you have volatile chemicals present, then obviously it is going to increase the vapor pressure at the sample surface, so we need to have a less heat of sublimation. So the material is going to melt, it is not going to form a frozen solid. If it forms a frozen solid, then it becomes easy for you to convert it into vapor by applying heat, but if it is forming an ice, okay, then it is not good, if it is forming a melted. So we need to dilute it with water prior to freezing. So by having water, more water, we can form solid ice, that is much better. So volatile chemicals always lead to problems in lyophilization. So what are the characteristics of the finished products? Once I have done some lyophilization, the amount of water, residual water present may be in the order of 1 to 3%. So the stability of the freeze dried products, it depends on the moisture present, oxygen, temperature. But if you are freeze drying vials and you have a good sealing system, you are preventing exposure to moisture and oxygen. So it is ideal to do small sample in vials, so we can seal them under vacuum. If you are storing material in high temperature, it will reduce the shelf life. So ideally refrigeration or freezing is always good for long term storage. So if you want to store blood or plasma, best thing is to freeze it or refrigerate it for long term storage, unlike storing it at high temperature. So if you have finished removing all the bound water, then there will not be any other water, it will have just very small amount of moisture present, which we call it the equilibrium moisture content. So we can call the freeze drying to be completed actually. So what are the advantages of lyophilization over conventional drying? So conventional drying I have been talking about before, like, so you apply vacuum, you apply temperature, so the water vapor evaporates and goes, whereas in a lyophilization or a freeze drying you freeze it so that the water becomes ice, and then you keep the temperature and pressure so that it does not go through the water phase, but it directly goes into the vapor phase. So you are operating below the critical point. So advantages of lyophilization is prevention of chemical and biological potency, so preservation of chemical and biological potency, you are maintaining it. Homogeneity of the final product, the product will be homogeneous. The advantage is ease of dispensing, metering before final package. You are preventing it from chemical degradation. You can rehydrate it very easily. For example, if you have dry powder fields like injectable penicillin, it becomes very easy rehydrated completely without any problem. So these are the advantages of lyophilization over that. So let us look at a schematic of a freeze dryer, how it looks like. This is a freeze dryer, it is a large scale industrial scale freeze dryer. So we have a frozen solid in a big container, needs to be dried. So we have the solid is frozen, ice is formed, that is water has become ice, okay. Then what do? You have a refrigeration system here, you have a vacuum pump here, okay. So the ice becomes vapor, comes down, it condenses here, again it forms ice on the wall. This is giving you the required vacuum. So you are applying vacuum here, at the same time this temperature is high enough for the ice to directly go into vapor, which is condensed here and collected here. Here you have a refrigeration system which keeps the temperature of the surface low. This is how a large scale freeze drying unit works actually. Okay. So we have seen different types of drying, the conventional high temperature drying and the lyophilization freeze drying type of system, where you are drying at a lower temperature, whereas in the conventional drying you are drying by applying heat. So this is one of the very important downstream process. It comes almost at the end of your downstream, where you are reaching the finished product stage, okay. So what are the disadvantages of lyophilization? It is pretty expensive, capital cost of the equipment is very high, it is 3 times more than traditional sterile solutions or sterile dry powder fill methods, because you need a refrigeration system, you need a vacuum pump, so many things, high energy cost, 2 to 3 times, long processing time, you need long time. If I am going for a conventional drying where I am applying vacuum and heating the material so that the water becomes vapor, I may finish it in few hours, whereas if I am going for a lyophilization or a freeze drying where I am freezing the material and then I am increasing the temperature, changing the temperature and pressure to remove the moisture and so on, it may take 24 to 48 hours. So instead of 4 to 5 hours I may go to 24 to 48 hours, okay. So these are the advantages of disadvantages of lyophilization. But then for high value proteins, peptides, vaccines, this is the only way to give stable biologically active products with long shelf life, there is no other go, you have to resort to this type of method, okay. Okay. So far we talked about different types of drying and what are the disadvantages and advantages of different types of dryings. So that completes another downstream operation. Let us look at another another downstream operation, and that is called the distillation. Distillation is also a very important downstream operation. If you want to separate metabolites or solvents mixture, the most important point here you need to keep in mind is they are not temperature sensitive, that means they can withstand higher temperature. In chemical engineering, chemical process and chemical manufacturing, distillation is widely used because it is very fast, quick, very efficient, and we can end up with high purity material. But in biochemical type of situation, because we are worried about the temperature sensitivity of the products, we generally do not resort to distillation, but we do distillation when we want to recycle or recover solvents. For example, in extraction I am using solvents for extraction, now I would like to recover that solvent so that I can reuse, I cannot throw out all the solvent, so I need to reuse, so I need to recover the solvent. I am doing washing, so in such case chromatography I am using lot of solvents, then I would like to recover the solvent so that I can reuse the solvent. So in such situations I need to resort to distillation, there is no other go, and it is, as I said, it is the most efficient and best method where you can get very pure product. So distillation has got many advantages, especially for recovery of solvents from chromatography, recovery of solvents from extraction, and so on actually. So it is good if you want to separate liquids having different vapor pressure. So the principle of operation is based on vapor pressure. So when I heat a mixture of liquid, the liquid with lower boiling point goes into the vapor, whereas the liquid with higher boiling point remains in the solution. By doing this, I am creating an equilibrium between the vapor and the liquid phase. I am creating an equilibrium between the vapor phase and the liquid phase. So the vapor will predominantly contain the low boiling and the liquid will predominantly contain the high boiling. Okay. So if I, for example, I have methanol water, I heat it up, there is a vapor formed, there is a liquid. So when I keep these two in equilibrium, and if I analyze the vapor, it will have more of methanol. If I analyze the liquid, it will have more of water, because methanol is lower boiling than water, more methanol will be there in the vapor phase and more water will be in the liquid phase. So if I condense the vapor, I will have more methanol in that vapor. So I can again once again take that mixture, again heat it up, condense the vapor, I will have more methanol and so on actually. So that is how I can recover all the methanol. So as I said, this type of distillation is very useful if you are working on recovery of solvent from extraction, recovery of solvent from chromatography, HPLCs and so on actually. So this is called a vapor liquid equilibrium diagram for a binary mixture. So suppose you have two components A and B, like ethanol water, methanol water. Okay. So this is how a vapor liquid equilibrium diagram, VLE we call it, vapor liquid equilibrium diagram for a binary mixture. So the x axis you draw the mole fraction of the low boiling compound. Okay. So x axis is 0 to 1, y axis mole fraction of the low boiling component in the vapor, again 0 to 1. Okay. So you will get a graph like this, a curve sometimes may be like this, okay, or sometimes the curve may be going concave down. So you may have a concave or you can have a convex. Now this is called the x equal to y line. Okay. This is called the vapor liquid equilibrium diagram. So if you take any point in this particular graph, this tells you the mole fraction of the low boiling compound in the liquid, and this will tell you the mole fraction of the low boiling compound in the vapor. Okay. So obviously, because I said that you will have more low boiling component in the vapor than in the liquid phase. So if you take a point and project it to the x and y axis, you will have more of the low boiling component in the vapor phase than in the liquid phase. Whereas if you have a graph which is very close to this x equal to y line, the amount of component, low boiling component in the liquid phase or in the vapor phase will be equal. That means that is called a constant boiling mixture. Okay. So if you have this, instead of this graph which is far away from the x equal to y line, if they are very close, then x will become equal to y. That means the concentration of the low boiling in the liquid phase or in the vapor phase is equal. So that is called a constant boiling mixture. So ideally, if I boil a binary mixture, I would like to have more of the low boiler in the vapor phase and less of the low boiler in the liquid phase, so that I can condense the vapor, which will have more of the low boiler. Whereas if the concentration of the component is equal in both the phases, then I am not achieving the separation. So that is called a constant boiling mixture, and a constant boiling mixture we cannot separate using a simple distillation at all. So we have two components, binary, and this particular graphs tells you the vapor liquid equilibrium for the low boiling. So obviously because it is a binary, one minus the other one gives you the concentration for the high boiling. So generally we do not plot for high boiling, we always plot the VLE diagram for the low boiler. Okay. Now there is another picture which brings in not only the mole fraction for the two components, but we also bring in the concept of temperature into this, and that is called a TXY diagram. That is called a TXY diagram. There we also bring in the temperature. Okay. Now let us start from this side, So we have A is 0, so B is 100. So when you go to the other end, we have A equal to 100 and B is equal to 0. Okay. And here you have on the y axis we have the temperature here. So you will have one graph corresponding to the vapor composition, another graph corresponding to the liquid composition. So here this corresponds to the boiling point for pure B, this corresponds to the boiling point for pure A, because here you have 100% A, correct, here you have the 100% A, here you have the 100% B. So this temperature corresponds to boiling point of pure B, this temperature corresponds to the boiling point of pure A. Okay. So you can have the other way also, that means in this particular picture we are showing that boiling point of pure A is higher than boiling point of pure B, but you can have another situation where the boiling point of pure A could be lower, boiling point of pure B could be higher. Okay. Now this graph corresponds to vapor, this corresponds to the liquid composition, this is called a TXY binary diagram. So if you take one point here, okay, so this is at a temperature T1 and then you project it down and then go again to the liquid and then project it down. So what does this mean? At a temperature T1 the vapor will have A2% of the species A and B2% of species B, whereas the liquid will have A1% of species A and B1% of species B. Okay. And here the boiling point of A is higher, so obviously A should be more in the liquid and A should be less in the vapor, correct, and boiling point of B is less than A, so the vapor should have more B and the liquid should have less B. Okay. Because B2 will be greater than B1 and A1 will be greater than A2. So you see, if we have a diagram like this, the TXY diagram, then at any temperature all I have to do is draw lines horizontal and I can tell what will be the composition of A and B in the liquid phase, what will be the composition of A and B in the vapor phase. So this is also a useful diagram. Whereas if you have a VLE diagram, it does not bring in any temperature aspect into it, but it just brings in the compositions. Okay. It just brings in the compositions of A and B in the vapor and liquid situation. So as I said, in this particular figure we are saying that the boiling point of A is higher, so A is a heavy material and boiling point of B is lower, so B is a light material. So more B is always found in the vapor, whereas more A is always found in the liquid, okay, in this particular figure. So you can have a situation like this, so you can have this up and this down. So in that situation we can say B is a higher boiler and A is a lower boiler. Okay. Now the same figure you can have different types of combinations, you can have the vapor like this, whereas the liquid may be going like this. you may have the liquid like this, vapor may be going up like this. Okay. So if you look here, or if you look here, the concentrations in the vapor phase and in the liquid phase are the same. I sometime back mentioned something, if they are same, they are called constant boiling mixture, or they are called azeotropes, that is the name for that, azeotropes. So we have a constant boiling mixture, that is an azeotrope. So this is a high boiling azeotrope, this is a low boiling azeotrope. If you see the boiling point of the mixture here is higher than the individual boiling points, and the concentration in the vapor phase and the liquid phase will be same, and here the boiling point of the azeotrope is lower than the individual component, pure component. So that is why it is called a low boiling azeotrope, and again the concentration of this mixture in the vapor and in the liquid phase are the same. So we cannot separate out this type of binary system because they have a constant boiling region here. So what do you do if you have azeotropes? There are different methods. You sometimes change the pressure condition so that azeotrope may go, or you sometimes add a third component so that it breaks the azeotrope, and nowadays we are resorting to even membrane type of situations where we can break azeotropes, because membranes do not work based on vapor pressure, membrane just work based on either size or molecular weight, solubility and so on actually. So there are pervaporation membranes which we talked about long time back, where we can use that type of membranes for breaking azeotropic situations. So how does azeotropes look in VLE diagram, the vapor liquid equilibrium diagram? So the azeotropes will look like that, x and y. So you may have, instead of graph going all the time above the x equal to y line or all the time below the x equal to y line, it will just cut at some point. Okay. If this graph all the time goes above, no problem, if it goes all the time below, no problem, but if it goes like this, then at this place we have the composition of the low boiler in the vapor and the liquid are equal, okay, because this is x equal to y line. Similarly here it will be x equal to y, so it is called a constant boiling azeotrope. So if you have the VLE diagram like this, or if you have the TXY diagram like this for a binary system, you can say they are having a they have azeotrope, so they cannot be separated by normal methods at all. So there are different types of distillation columns we can use, you know, and they are called tray columns, plate columns, packed columns. So we can have packed material inside the distillation column, we can have plate type of material, or we can even have trays type. So all these help in mixing the vapor and the liquid together, bringing them in close contact with each other, thereby you can get a better separation. So these are the main advantages of that. So if you have a mixture, two components, an ideal mixture is the one which obeys Raoult's law. Okay. So like hexane and heptane, benzene and methylbenzene, propane 1-ol and propane 2-ol, so they are called ideal. So they all obey the Raoult's law. So what does this Raoult's law state? So what it says is the partial vapor pressure of a component in a mixture is equal to vapor pressure of the pure component at that temperature into mole fraction in the mixture. Okay. Okay. So if you have a binary system, the partial pressure of A is the vapor pressure of the pure component into mole fraction of that component present in the binary mixture. Similarly, partial pressure for B will be equal to pure component vapor pressure of B multiplied by the mole fraction of B present in that. Okay. So this is a very important law, because it tells you that the partial pressure exerted by a component is a function of the mole fraction in that mixture, binary mixture, as well as its vapor pressure. So if the mole fraction is high, the partial pressure is high. If the vapor pressure is high, then the partial pressure is also high. Now at the same time, the total vapor pressure of this mixture will be equal to Pa plus Pb, because Pa is the partial pressure offered by A, Pb is the partial pressure offered by B. So Pa plus Pb is equal to total vapor pressure. So if you are talking about operating at atmospheric pressure, so Pa plus Pb will be equal to atmospheric pressure. And also Xa plus Xb, that is the mole fraction of A plus mole fraction of B, is equal to 1. If it is a binary system, obviously this also should be true. Okay. So this Revolt's law tells that if I know properties of one, I can calculate what will be the partial pressure of that particular solute. So this is a typical batch distillation column. So what do? We charge material in a reboiler, okay, and then we heat it up. So the vapor travels up, and then the lighter products keep coming up, it gets condensed, it gets removed. Sometimes there is a lighter gets condensed here, they may come down as a liquid, vapor rises. So this is a column, we call it a column. It can be a packed material inside, or it can be any type of material inside, which brings in a good mixing between the liquid that is coming down and the vapor that is rising. Continuous distillation column. So as the name implies, continuously you are feeding some mixture and the heavy material comes down, it is heated up as a vapor, so it rises, the vapors get condensed, and then the light product is removed. Part of the condense is sent back, that is called a reflex. Okay. So the liquid travels down, the vapor travels up. So by this particular operation, what do? We are bringing the liquid and the vapor in contact with each other. So by bringing in this particular contact, we are achieving the movement of the vapor into the liquid phase, that means movement of the low boiling that is present in the vapor to rise, and movement of the heavy material to come down the column. So by doing this operation, we will have more of the heavies here, that means high boiling material, and we will have more of the light material here, that is the low boiling material. So we can play around with the reflex and achieve very good separation. But then if we reflex too much of the vapor down into the column, we are slowing down our distillation, we are increasing the energy requirements and so on actually. Whereas if I reduce the reflex, then my separation efficiency goes down. So I have to keep playing with both these factors so that I achieve good separation, and at the same time my energy cost does not go up. Okay. So that is where we play around with the reflex. We can have different types of packing material inside, like I mentioned before. We can have tray column, we can have packed column, we can have sieve plates, different type of plates. So we can bring in a good mixing between the vapor that is rising and the liquid that is falling, so that the efficiency of separation is also enhanced. So these are different ways by which we can bring in purification and recovery of solvents or other liquids which we want to recycle back into the process. So distillation is a very useful technique to practice, especially as I said in a chromatography, for recovery of the solvent which you use in the continuous phase, or in the extraction process if you are interested in recycling the solvent which you use for extraction. So you need to understand how the distillation system works, and distillation has been there in chemical engineering for almost 70-80 years. So the technology is well established, so it is easily and quickly adapted in the biochemical industries as well, without adding any extra research effect into it actually. And as I said, if you are handling a thermally labile material, then obviously distillation cannot be resorted to, because when you are operating at higher temperature, when the material gets either deactivated or becomes a tarry type of product. So having talked about distillation, having talked about drying and lyophilization, we will in the next class see what are the various types of downstream that are still pending.